Okay, today let's look at chemical equations. These are things that you've probably seen before, but the first thing I want to draw your attention to is the equation part. Something is being equated here. So one side is going to be equal to the other, and that's an important detail to remember. The first thing that I want to show you is how you would read a chemical equation. On the left side, you always have the reactants. And typically you have more than one reactant, but for right now I'm just going to have reactants on the left. And then you have an arrow leading to products. So you would say these reactants react to yield products. Okay, so let's look at an example to make this a little bit more tangible. First we have CO2 reacts with H2O to yield C6H12O6 plus O2. Now this equation might look a little bit familiar to you if you remember anything from biology, because this is the equation for photosynthesis. And if you remember, carbon dioxide, that's CO2, H2O is water, C6H12O6 is glucose, and O2 is oxygen gas. Keep in mind, oxygen is a diatomic element, so you would never just have oxygen by itself, it would be O2. Now, the idea behind equation, the fact that something is equated here, is that everything on the left side, everything on the reactant side, must equal everything on the product side. And what that means is that you should have the same number of carbons and oxygens and hydrogens in the reactant side as you have carbons and hydrogens and oxygens on the product side. Now, there's a couple of ways to balance a chemical equation, which is what we're about to do. And I think the easiest one for students to use as they're getting used to the process is the inventory method, where on each side you're going to count up how many of each element you have. So first of all, we've got carbons, oxygens, and hydrogens. So carbons, oxygens, and hydrogens. And you have the same thing on the product side, carbons, oxygens, and hydrogens. And we're going to count them up. So here you have one carbon total on the reactant side, so that's one. As far as oxygen, notice that you have oxygen in carbon dioxide, but there are two of them. So don't forget that subscript. You have two oxygens here, and then in water you have one. So that's a total of three. And for hydrogens, you have two. Again, don't forget about that subscript. You have two hydrogens. Now looking on the product side, if you're looking at carbon, notice the subscript. There are 6 carbons in the products. Oxygens, you've got 6 in this glucose, but remember you also have 2 here, so there's a total of 8. And then for hydrogens, you have 12 hydrogens. Okay. Now notice that this equation is very much not balanced. Remember, you're supposed to have the same number of carbons, oxygens, and hydrogens on the reactant side as you do on the product side. Now, you can usually just start anywhere. I'm going to look at the carbons first. I see here that on this side I have 6, and on this side I have 1. Now, keep in mind that you cannot change the subscripts. The subscripts are part of the molecule. You can't change what kind of molecule you have at this point. You can only change how many of each molecule you have. So if I look at 6 carbons here and I need 6 here, I'm going to need 6 molecules of carbon dioxide. So I'm going to put a coefficient here. The 6 means that I now have 6 molecules of CO2. So now I have to change this because I no longer have only 1 carbon, I have 6. But also, I now have more oxygens. So remember that every molecule of carbon dioxide has 2 oxygens. And since I have 6 molecules, I'm going to multiply this 2 by the 6. So I have 12 oxygens here plus the 1 over here. So 13 oxygens. Okay? Again, our carbons now are perfectly happy. Oxygen's not so happy, hydrogen's not so happy. Now, balancing out these oxygens, 13 to 8, that's going to be a little tricky. So let's move on to the hydrogens and see if we can do something there. If we have 12 hydrogens on this side and 2 hydrogens on this side, what can we do with this molecule, or how many of these water molecules do we need to balance out the hydrogen? And again, you're just dividing. If you have 12 here, 2 here, then 6 water molecules will give you 12 hydrogens. So now we've got 12 hydrogens. But again, notice that that has changed our number of oxygens. All right, so let's count up our oxygens again because it's not 13. Remember, we have 12 here, 2 times 6. And now, how many do we have in this water molecule? Each water has 1 oxygen, and we have 6 waters. So that's another 6. So 12 plus 6, we now have 18 oxygens. Okay. Now, notice that we have not changed anything on the product side. And at this point, since our carbons are balanced and our hydrogens are balanced, we don't want to change the number of glucose molecules. So we're going to keep that the same. We're just going to leave that because we really don't, already that's perfectly happy. What we do need to change is how many oxygen atoms we have. And right now, we have 6 in the glucose molecule and 2 over here, and we want 18. So remember, we're not going to change our glucose, so we've got 6 there. That means we're going to need 12 more oxygens from just oxygen gas. And in order to do that, considering each molecule of oxygen has 2 oxygen atoms, we just need 6 oxygen molecules. And let's check our work here. Now we have 6 times 2 is 12. Plus 6 times 1, which is 6, that equals 18. So now we have 18, which is equal to 18 here. And this equation is now completely balanced. Okay, and you can check it just to make sure, but now we have a coefficient in front of each molecule. And if I were to read this, I would say 6 molecules of carbon dioxide react with 6 molecules of water to yield 1 molecule of glucose and 6 molecules of oxygen gas. That would be the appropriate way to read this equation. Now, in the next couple of videos, I will show you some additional examples, and I just need to warn you that more than likely I won't give you the formula like this. I will ask you to write out the chemical formulas based on names. So we'll do some practice with that as well.